So good afternoon, everybody. I hope that you enjoyed lunch, and I will try to speak so that you will not fall asleep. So I should speak about fuel cycle. I will speak a little bit less about MSR and more about the fuel cycle, but I will probably address all the important uh, features of MSR and fuel cycle. So first of all, what is actually fuel cycle? If you think about it, I did this exercise, I come to something like it's a process chain to obtain energy. And I use this example like a fusion driven closed fuel cycle. But this is not what you expect to hear today. So the fuel cycle we should speak about is the nuclear fuel cycle, and it has two halves. It has front end and back end. Front end is everything connected to mining, fabrication, enrichment. The back end is storing of the irradiated fuel, reprocessing, partitioning, and waste disposal. I will address none of these two. I will look what happens in the middle. So my presentation will be about the neutronic aspect of the fuel cycle. So what happens if you irradiate, and which consequences the recycling may have to the reactor physics of the reactor. Now, what is actual nuclear fuel? So if you want to see what is nuclear fuel, let's start really from the basic, from the bottom. Let's look on the periodic table. You have three groups of elements. You have elements from Big Bang, you have elements from stellar and from supernova nucleosynthesis. And from these, our fuel are the actinides. You see them here. And the reason why actinides are our fuel is based on the binding energy of the nucleons in the nuclei. So maybe you have seen already this chart. It's well described by the liquid drop model. I will not go to the detail, but basically, if you want to produce energy, you need to increase the binding energy. And there are two basic ways. One is fusion, and the biggest issue of fusion is that there is a Coulombic electrostatic repulsion, so you need to overcome this repulsion. Or you can do fission, and in case of fission, it's the opposite. The Coulombic electrostatic repulsion is the main source of energy. This is the force which accelerates the fission products and produce the energy, actually. So it's actinides, what is fissile, and which can produce fuel. Nonetheless, they are all unstable. They are all unstable, and if you carefully look on this chart, it's a logarithmic scale. There are three with fairly long half-lives. You can guess which three these are. It's the longest half-life has thorium-232. I will call it thorium-2 from now on. The second longest is uranium-8, and the third longest is uranium-5. If you see the half-lives, you can easily guess that the reserve of these elements differ. So for 1 kilogram of uranium-8, we have 3 to 4 kilograms of thorium and only 7 grams of uranium-5 in the Earth. And unfortunately, uranium-5 is the only one fissile. Now, the half-lives of uranium-5 and 8 are different. So if you think about it, the share was evolving. So you can do the calculation, do the curve, and you immediately see that in the past, in the Earth history, there was higher enriched uranium. And we know now that there was water-moderated natural reactor in Oklo around 1.7 billion years ago. But the question would be, of course, why not earlier? Because earlier we had higher enrichment, and the answer is chemical. There was several dissolution precipitation processes necessary, so it took time. But still, at the very beginning, this is in even fast reactor grade uranium. You can think about what if there was a place where the concentration was faster, and indeed it may be the case that the outer core of the Earth enabled the concentration much faster, and it may be that there is still ongoing fast reactor in the Earth core. We have several, let's say, indices that it may be the case. But the main message of this slide, we have unfortunately only 0.72% of uranium-5. So the stockpile, what we have, if we speak about sustainability, are the actinides which are from supernova explosion. So they are definitely not renewable. We cannot wait for the next batch of actinides. So the aim of the fuel cycle, if you speak about sustainability, is the maximum utilization of the resources and the Relative share of resources we have is illustrated here, and unfortunately it's only uranium-5 which is fissile. So this is the first kind of scientific chart. You saw many of them already today and yesterday. This is energy of the neutron in electron volts, and this is the probability to cause fission. So only in uranium-5 case you can cause fission even with thermal neutrons, low energy neutrons. For thorium and uranium, you need a high energy of neutrons, but let's call them fissionable because you can still fission them. And it's good to say that the neons between them is small, but still uranium-8 is 5 times more fissionable when you have fast neutrons. But these elements are typically transmuted. They capture the neutron and they are transmuted. If we speak about natural uranium, it can be used in a reactor, but then you need a heavy water moderator or a graphite moderator. Typically what we do, we enrich it to 5% and use light water. But in this case, already at the beginning, you have 90% of the natural resources left outside. But you can also enrich it to 20% and use it without a moderator in fast reactor. You can imagine the reactors for each category, like CANDU for heavy water, light water reactors for the enriched uranium, and fast reactors for the 20% enriched uranium. And in each of these reactors, you can reach certain burn-up. In CANDU, let's say 0.75%, light water reactor 5%, fast reactors maybe 10%. So the question is how much of natural uranium you utilize in these reactors. And it is actually so that in CANDU, where you directly use natural uranium, it is the same number. In light water reactor, because you let 90% in the enrichment factory, it's 10 times less, so it's 0.5%. And in fast reactor, it's even worse. So none of these reactors, if it is fueled by uranium-5, is sustainable, because we cannot use more than 1% of the resources we have. So the way to go around is somehow to use the two fertile elements, uranium-8 and thorium-2. So if you look on the fission reaction, you definitely need one neutron to maintain the chain reaction. Now you would like to use the other neutron to breed, to use the fertile elements and to produce something fissile. And actually the fissile, the outcome of the reaction may be the same as the initial one, so you can say it's catalyzer. And the reaction is actually good for catalytic burning of these two fertile elements. And that's it, happily ever after, yes. But there is a problem. There is a problem. There is a very tight neutron economy. What is left for the losses is everything which is above these 2 neutrons you need. These synthetic elements produced by neutron captured and 2 consecutive beta decays are uranium-3 and plutonium-9. They are both fissile, and therefore we call this neutron capture a breeding. If you look on the fission probabilities, they are fissile by thermal neutrons. They are quite high, and especially for uranium-3, it's around 90% for all the energies, and this is the biggest advantage of thorium cycle. If there would be not this case of this probability, the thorium cycle will be not so appealing. At the same time, if I speak about it, I should say that the chart was produced by Jeff's 3.1 library. If you use the NDF B7, it's slightly worse here, but still, uranium-3 is the best. And nonetheless, all 3 of them may fail to be fissioned and may capture a neutron. If they capture a neutron, they produce another element which is not fissile anymore again. It's fertile element. Let's call it secondary fertile. You see it here. The products are here, so they are fertile again. And in this case, it's a parasitic capture. And furthermore, I would say you will need one more neutron to get rid of these fertile elements. So when the fission fails, you lose 2 neutrons, basically. The question, if fissile or fertile, there is some regularity because you transmute fertile to fissile and fissile back to fertile. If you go back to the liquid drop model, there is a simple pairing effect for each nuclei. So the neutrons want to be in couples. And actually the interacting neutrons, which is interacting with the nuclei, brings different binding energy according to how many neutrons are already inside. So in case of thorium, when you have even number of neutrons, the next neutron is not so welcome, so the binding energy is not so high, and you don't overcome the fission barrier, so it's not fissile. In case of thorium-3, which is the intermediate product, it is slightly fissile. Protactinium-3 is not fissile, uranium-3 is fissile because you have even an odd number of neutrons in them. And you can continue, uranium-4 not fissile, 5 fissile, 6 not fissile. There is some regularity nonetheless. If you go for higher nucleus, the fission barrier is weaker and weaker. So at the end, it's not so black and white if yes and no, because there are also spontaneously fissile elements. Yes, so for the higher elements, let's say plutonium 41, 42, 43, the fission chance is there even though they should be fertile, according to this logic. So the two cycles, two main cycles we can have is uranium-plutonium cycle and thorium-uranium cycle. Main fertile is uranium-8, thorium-2, main fissile, plutonium-9, uranium-3. Secondary fertile, plutonium-40, uranium-4. And already by the secondary fissile, the cycles slightly differ because plutonium-41 can beta decay, uranium-5 not, and so on and so on. If you look on the position of plutonium in these two cycles, we say very often that thorium cycle produces less minor actinides. What is true. Nonetheless, if I show you some half-lives here, the thorium cycle is not so innocent. Uranium-3 and 4, they don't have so long half-lives to decay. They are long, but still the decay chain. Yes, the decay chain. The decay chain of all the daughter products will be still there. So assuming that you have the same reprocessing losses, thorium cycle will be slightly better, but I would not say that everything is solved with that. So what was not in the previous picture is the intermediate product, and I would like to address here one thing. Even the intermediate product like protactinium-3 or neptunium-9 may capture a neutron and create a secondary fertile. And actually, after certain time of operation, the capture reaction here will equalize by the decay reaction here. And since the half-lives are different, it will end up so that there will be equilibrium which will be different. And this is roughly 1 to 11. So finally, we will have 11 times more protactinium in the comparable cycles. This is not an advantage because protactinium may capture a neutron, but the molten salt reactor can avoid this parasitic capture because from one perspective, the part of the fuel can be outside of the reactor. From another perspective, you may think about separation of this protactinium and let it decay outside of the flux. Now, this was about the chains. The question is how many neutrons we have available in the system. And this is given by nu bar, so the average number of neutrons per fission. And in this category, in discipline, plutonium-9 is dominating. So this is the biggest advantage of the plutonium cycle. There is more or less 2.9 neutrons flat for each spectrum. The second best is uranium-3 with only 2.5. And there is, of course, uranium-5 and the fertile elements which produce even less. And since I speak about fuel cycle, more or less I cannot avoid this kind of obligation to speak about eta. Eta is a neutron generation factor. It was introduced by Fermi in the famous 4-factor formula for thermal neutrons and the fuel as a whole. But nowadays often used to discuss single isotope breeding capability. And in this case, it's simply a product of these two values I already showed you. So you have a fission probability and average number of neutrons. And now you have a high fission probability for uranium-3, but low production of neutrons, compared to slightly lower fission probability multiplied by higher neutron production. Before I show you the eta chart, you already have seen it this morning. Let's recall that you need 2 neutrons, one for the fission reaction, one for the breeding. So you should compare eta with the number 2, which is done here. And then we can discuss about the reactors. What is actually quite important is this slope is pretty straightforward and is determined many features of the fuel cycle, and it determines also the safety features, because every time there will be spectrum hardening, either by fuel cycle or by accidental conditions, you will improve the neutron economy. At the same time, for uranium-3, it's pretty flat. So this enables you to make even thermal breeders, which is not possible in plutonium cycle because you probably will not pass through this area, and then it's not self-sustaining in the thermal area. This is, in my opinion, not the full story, because we know that uranium-8 can be directly fissioned, and it can be up to 10% of the fission reaction, so you should reduce the two line to 1.9 for uranium cycle. And second of all, there will be these secondary and tertiary products of the captures and so on, and they will have different properties than the initial fissile. So this will modify the picture. So eta is nice, but doesn't say everything. Now we speak about fuel cycle sustainability. We speak about Gen 4 reactors, and the sustainability is a feature of Gen 4 reactors which may conflict with the other features. For sustainability, you need first of all to reduce the waste and to increase the resource utilization. For this utilization, you definitely need isobreeder reactor, typically with fast neutron spectrum. With fast neutron spectrum, you may have safety issues. For both breeding and waste reduction, you probably will need fuel recycling. And fast reactor with fuel recycling may jeopardize your economy. And whenever you will recycle the fuel, you may have problem with proliferation. So we added new goal compared to current reactors, and we may have issue with the 3 points which were fine, relatively fine with the current neutrons reactors. MSR may have the advantage that in long term, once you develop it and well understand, may combine these four without compromise. So this is probably the only reactor which may provide this advantage. Now sustainability is tightly connected to recycling, but recycling alone doesn't mean sustainability. Even if you will recycle all the fuel, you may not achieve high sustainability in the case that there will be enriched uranium or makeup fuel used in the feed. In this case, the sustainability will be limited. And if you look on this chart, let's take the case of 5% enriched uranium. Even if you completely burned the uranium, 5% enriched uranium, so completely burning 100% of the fuel, the sustainability will be only 10% because the remaining 90% will be in the enrichment facility. So whenever you use enriched uranium as your feed or makeup fuel, your sustainability will be very limited. Nonetheless, if you recall that the current reactors can burn at maximum 0.7%, then sustainability around 10 or 20% is still something. Another thing is, even if you will recycle natural uranium or thorium, there will be always reprocessing losses. And there is another chart which is function of the reprocessing frequency, or let's say the discharge burn-up of the fuel which you are reprocessing, and show several reprocessing losses. And for typical fast reactor, you reach the burn-up of 10% of the fuel, and then you see the current technology which reprocessing losses it has, and this gives you the natural resources utilization. So if you don't recycle minor actinides, for instance, and you have 0.1% reprocessing losses, maybe you are somewhere around 95%. But you should be very careful. You should be very careful with MSR or other reactors. If you are reprocessing fuel which is slightly burned, so the fission product share is small, then you should have really efficient method, because otherwise your natural resources utilization may be smaller than 80%. And this is actually a homework for you, because this is a lecture. Please cross-check that the derivation is correct. Yes, there will be one or two more homework. So, yes. So sustainability and safety. For sustainability, more or less, you need fast neutrons. With fast neutrons, you don't need moderator. The coolant is not having the function, and in this case, you can have a positive void effect, or it can be that core compaction produce positive reactivity. Then you have 3 fast Gen 4 reactors. I will very swiftly go through them. It's a gas fast reactor. The void effect is relatively small. Nonetheless, the coolant is pressurized, and depressurization is a safety issue because it's a question how to cool it after. In case of SFR, the void effect is strong, but it may be minimized by the core design, but still sodium may have rapid reactions, may burn. LFR has very strong void coefficient, but it's not so easy to void the core. At the same time, lead is very heavy, you may have safety problems from seismic, so to say. Generally, SFR and LFR, the liquid metal cooled reactors, have also some retention capabilities for the fission products. So when we do some claims for MSR, we should recall that these reactors may have something similar in accidental conditions. And last but not least, MSR, you have coolant and fuel together in one liquid. So definitely you can design the core with negative coolant density effect, and you can prevent the compaction or collection of the fuel by design. There are two basic issues related to sustainability actually. One is how to start the sustainable reactor, and the second is how to maintain it. The maintenance means you need a reactor which is capable to operate with equilibrium fuel composition, that all these secondary, tertiary elements are built up. And the second is that you need to have a method to separate the fission products from the reactor, which actually in all industrial technologies you call recycling, but in our technology we call it reprocessing. So how to start it? I have only 2 slides or 3 slides on it, even though it's a very interesting topic. We cannot rely on anything else than natural uranium or enriched uranium at the beginning. In the secondary stage, you have also plutonium, so you can use plutonium with your uranium if you aim at uranium-plutonium cycle. Then you can partially close the fuel cycle, recycling plutonium with uranium, or fully recycling also minor actinides. In case of thorium cycle, you are led by enriched uranium or plutonium. There is no other way how to irradiate thorium. In the secondary cycle, you can already have uranium-3, and of course you can then close the cycle so that you recycle only uranium. It's uranium-3 here, but it's all the uranium vector. Or fully closing the cycle if you recycle also minor actinides. Now to illustrate it a little bit more on one case, let's say that you have a reactor which needs to have 10% enriched uranium to be critical. If you want to start uranium-plutonium cycle, you are fine. You can directly use this fuel. So you have 10% enriched uranium, and this is your startup fuel. You can also use plutonium from light water reactors roughly with the same share, and everything is fine. If you would like to start thorium cycle, then it's not so easy, because to keep the same share of fissile, like here, you need to use 20% enriched uranium, and then you will have more or less only half of thorium in the system, so it will be mixed cycle, half-half. If you want to put more thorium, you need to enrich the uranium up to 90%, which is not allowed anymore nowadays. Or you should use plutonium from light water reactors, or even maybe fast reactors, who knows. But then there is an issue if you are aiming at fluoride salt reactor. Not all of the fluoride salts have enough sufficient solubility for this plutonium. So it's relatively an issue how to start the thorium cycle, because there are limitations in several cases. And what we are aiming at is the equilibrium cycle, where finally you have own plutonium vector in uranium-plutonium cycle, and you build a lot of uranium-3 in the thorium cycle. So this was about how to start it. Now, if you speak about how to maintain it, you need to have sufficient neutron economy. And you can say that neutron economy can be divided into 2 or 3 steps or stages. If your neutron economy is not enough, you have a converter. In this case, the fuel amount you load to the reactor is smaller than the fuel amount in the discharge fuel. Typically it's PWR or this integrated MSR. They works in converter regime, and typically it's open cycle. Yeah, you can recycle, but then as I showed you, the natural resources utilization may be 10–20%, but not more. In case of breeder, the fuel you load to the reactor, the content of fissile, is equal for the discharge fuel or even slightly higher. And then in this case, it has no sense to operate it in open cycle. You should definitely close the cycle and recycle it. And if you want to start the reactor, you need to use more or less average fuel, which has roughly the same content as here. The last step of neutron economy, let's call it breed and burn. It's also super breeder, where you don't need to have any fissile in the initial fuel, and you have a lot of fissile in the discharge fuel, and you produce the fissile in the reactor on the run. So the already irradiated assemblies produce enough neutrons to create a new fissile from the inserted assembly. And to initialize this reactor, you need average plutonium or content in the initial core. So now, if you want to assess if a reactor is converter, breeder, or breed and burn reactor, you should evaluate the performance in equilibrium closed cycle. So we did that actually when you fixed all the fuel cycle properties like the power, the reprocessing scheme, the feed, then it converges to an equilibrium composition, and reactivity and mass flows are stabilized. So I have here an example of the chain. Jan-Len already showed it this morning. So you have thorium-2 transmuted to uranium-3, then it goes further. If the fission fails, you have 2 neutron captures to create uranium-5. If the uranium-5 fission fails, then you go up to the plutonium-8 or 9. And in equilibrium, all this chain is stabilized and all the reactions are in balance. And what I want to show here is that the gateway for higher actinides is plutonium. If you compare it with uranium-plutonium cycle, then you are immediately there. But you can also say that, for instance, the end-to-end reaction on uranium-8 is not so dangerous because you go just this way. Whereas we know that in thorium cycle, it leads to uranium-2, which is not so nice because of the hard gamma emitters in the decay chain. So back to the topic, we would like to evaluate the neutron economy based on equilibrium cycle. We actually, or let's look now on 16 reactors in closed equilibrium cycle. So 8 thermal, those are salt-cooled pebble bed reactor, helium-cooled pebble bed reactor, RBMK, CANDU. 2 cases for graphite moderated MSR, it's FlyB salt and Fly, lithium beryllium salt. Then high performance light water reactor and normal light water reactor. These were compared with 8 fast reactors. So it's MSFR. Then there is a version of MSFR with the lithium beryllium salt. And the lead cooled, sodium cooled, and gas cooled fast reactor. Then the sodium cooled reactor with metallic fuel, and then 2 cases of chloride. So eutectic with sodium chloride and just the actinide chloride salt. This is a little bit academic case because the melting point is very high. Nonetheless, there exists eutectic of actinide tetrachloride and actinide trichloride. Questionable, but maybe there is something on it. Simulating these reactors, we had a very simplified assumption. So it was infinite lattice. Burn-up was given by discharge, burn-up, and irradiation time. Specific power was given by discharge, burn-up, and irradiation time. Fission products were neglected, no reprocessing losses, and continuous feed of the fertile thorium-2 or uranium-8, and ENDFB7 nuclear data library. So with this assumption, you get an equilibrium, and in the equilibrium you should have sufficient reactivity excess so that you can compensate for the neglected reprocessing losses, neutron leakage, and fission products parasitic captures. So the main result basically is the reactivity excess. It's quite complicated chart, and I can spend another lecture just explaining it. But let's focus on the most important things. So there are 3 MSR reactors, typical MSR reactors. Is the Oak Ridge type graphite moderated FlyB reactor, is the SMOFR MSFR, and let's say this as a sodium chloride reactor, fast reactor representative. So first of all, there are some reactors with thermal spectra which work, can be used for a closed fuel cycle in thorium. The MSFR salt provides slightly worse results than the other fast reactors. The chloride salt slightly better. Nonetheless, all the results are not so breathtaking. We are here about 10,000 PCM of reactivity excess. The hypothetical reactivity, if there wouldn't be any parasitic capture in the reactor, is around 20,000, and it's step by step reduced by each isotopes. And you see, if there wouldn't be structural materials, it would be possible to breed more or less in all thermal reactors. Now, you are surely interested to see how this was calculated, and there is the equation, simple neutron balance equation with 4 conditions. This condition is really a little bit tough to understand, so this is the second homework. Please try to derive this equation again if you would like to understand. Basically, you end up that with something like reactivity is equal reactivity excess from available neutrons, bonus from the fertile, thanks to the direct fission or end-to-end, and then parasitic captures. Let's compare it with plutonium cycle. So again, 16 reactors, equilibrium cycle, infinite lattice. It doesn't work in thermal spectrum. The parasitic capture of plutonium-9 and 40 and so on, it's too high in thermal spectrum. Even though the hypothetical excess reactivity is really high, it doesn't work. So that's clear. MSFR in the uranium-plutonium cycle produced more or less the same reactivity, around 6,000 as before, but is much worse than the classical solid fuel fast reactor, and then the chloride salt provide equal, let's say, comparable reactivity as the solid fuel fast reactors. Here is a statement where I say that uranium-plutonium cycle has better neutron economy. There are many neutrons to waste, but partially they are also really wasted. And thorium cycle has better neutron efficiency, because there are not so many neutrons, but they are relatively well used. So now we have this reactivity excess, and there is a case where we compared 8 salt reactors, and we include the fission products. So it's still infinite lattice, but fission products are in. And it's side by side, thorium cycle, uranium cycle for the 8 selected salts. And more or less the conclusion is, if you think about uranium-plutonium cycle, yes, let's use probably chlorides, enriched chlorides. There are some options for fluorides, but none of them is really breathtaking. If you want to use thorium cycle, there are 2 optimums. One is the fly salt, so a MSFR reactor, or then again you use chlorides. Saying that, some of the salts provide reactivity excess high enough to think about the breed and burn mode. So the breed and burn mode is that you are loading to the reactor only the fertile material, no fissile, and the fissile is produced firstly in the reactor. And later on, with burning of this produced fissile, you have excess neutrons so that you can again breed fuel from the introduced fertile element. In solid fuel reactor, it looks like this. You have a fresh assembly without fissile, then you burn it stepwise, and at the end you discharge the most burned assembly. Unfortunately, in MSR case, it's slightly different, because you load the fresh assembly, everything is mixed, and what you discharge is the average fuel. It's not the most burned fuel. So the distribution of burn-up is different between these 2 cases. It's like this in solid fuel reactors, and in liquid fuel reactor, it's you can have fuel which is theoretically you can have fuel which is there forever and has really high burn-up, but everything is mixed. This is just the theoretical distribution, but nevertheless it describes the composition. Now, using these 2 distribution functions, you can derive a model, and you can finally say that the K infinity, because it's a study on infinite lattice, of the breed and burn reactor is the probability of burn-up distribution multiplied by K infinity of a single cell which was irradiated from 0 to infinity. So it was more or less like irradiation on cell level, evolution of K effective or K infinity, multiplied by the distribution function. And then the T is here the variable. So for different T's you can plot the K effective, and it looks like this. So more or less this is the discharge burn-up in the breed and burn mode. It is function of T. So T is more or less here indirectly. And you see that the chloride salts definitely work. There is a chance to do breed and burn reactor with chloride salt. And uranium-plutonium cycle is much better because there are many neutrons available, and it's very hard spectrum, so you have no so high parasitic capture. In thorium cycle, you need fissile support. So we have been looking on a case where you have thorium with 5% plutonium inside, more or less to look on pseudo Britten burn like reactor used for plutonium burning. And this is the discharge burn up once again, so you can probably go up to 25% burn up with this Britten burn cycle. So once through cycle, which has up to 25% of natural resources utilization. Yeah, okay, I say 25, here is 20. It's changing. So the problem with Britten burn is that chlorides are transparent for the neutrons. Again, comparing 16 reactors, here we have the actinide's density and migration length in each of these reactors. And as you see, chloride salts reactors are the second worst, just after HDR. So to minimize the leakage, they should be really, really big. So that's really the biggest disadvantage. And I put here a kind of illustrative picture where you have the MSFR, sum of R core, like 2 by 2 meters. And for Britten burn in chloride, you need at least 4 by 4. If you calculate the volumes, it's really a different story. So 9 cubic meters versus 50 cubic meters. So far, I think from the neutron economy, the last thing I would like to address is the problem of maintaining the chain reaction. In the ideal case, you would like to have a kind of never-ending fire, fertile elements as the wood, producing energy, but the problem is that it works only if you remove the fission products. And we have established a method, but this is necessary to remove the fission products. It's necessary because fission products absorb neutrons. And then you have highly radiotoxic fuel which needs to be reprocessed. We have established a technological process for uranium-plutonium cycle aqueous reprocessing. There is an issue if you would like to recycle minor actinides because they produce a lot of heat and they emit neutrons, so it's not so easy to fabricate pellets in this case. And the similar technology for thorium cycle is more or less missing. It's not that it's impossible, but there is not so big technological experience. And in thorium cycle you have a lot of hard gammas from the uranium-2 decay chain, so this may be another issue. You have the same in plutonium cycle, but it's slightly more in thorium. Therefore, recycling of thorium may be demanding. You need to shield even the fabrication unit. Again, speaking about MSR, if you have liquid fuel, the accommodation of minor actinides may be much more easier. And even the hard gamma, probably the liquid is easier to treat in the reprocessing facility than solid fuel. Fission products are absorbing a lot of neutrons in thermal spectrum. In fast, it's less sensitive. The question is why? And of course, the immediate answer would be yes, the cross-sections are higher in thermal spectrum, but the cross-sections are higher for all isotopes in the core, so why fission products? This argument is still true because fission products have higher cross-sections, but there is another reason. The fission products to fuel ratio in typical moderated burner like LW or HDR on this figure, thanks Fanny, there is the initial fissile load between 5 to 8% of uranium-5, and if you discharge it, there is only 2% left. In the fast breeder reactor, you put inside 10% of fissile element and you discharge 10% of fissile element, so it's flat, always staying around 10%. And now the fission products are created in the core, so at the end you have 5% of fission products and only 2% of fissile left. And in fast reactor you may have 10% of fission products but still 10% of fissile left. So the ratio between fission products and the fissile is strongly different between fast breeder and thermal burner. So therefore we say that the fission products are more visible, or the thermal reactors are more sensitive to fission products. There are two different effects. Why you should speak about fission products and irradiation? So if you have solid fuel, you have more or less 4 points why you have limited irradiation time. It's the cladding lifetime, is the fissile element load. In case of burner, is the gaseous fission product production, and is the core poisoning by fission products. In liquid fuel reactor, you don't have cladding. In case of breeder, you are self-sustaining, and in case you can add continuously thorium if needed, the gaseous and volatile fission products are removed, so only the remaining fission products are still poisoning the core. And actually, the fission products are the only reason why we need to reprocess or recycle the salt. Now, the components of the salt, it's the carrier salt, are the fertile actinides, fissile actinides, the byproducts, the minor actinides. We are fine with them, they can stay in the core, just the fission products are disturbing. But if you want to remove them, actually, usually it's the last component which goes out from the salt. So you can use several different methods, techniques, but usually the fission products are one of the last getting out of the salt. So now, since you remove all the salt from the reactor, the question is what you should recycle and why. And there are three motivations what to recycle and why. From reactor physics point of view, it is only important to recycle the main fissile, so uranium-3 or uranium vector or plutonium vector. We have enough thorium to add extra thorium. We have probably enough of carrier salt, even though it may be expensive. So from reactor physics point of view, it's only necessary to recycle the main fissile. From sustainability point of view, sooner or later you should recycle also the main fertile, thorium and uranium, maybe also some rare elements. And from economic point of view, it's always a question of price. Maybe it's cheaper to recycle everything, maybe it's cheaper to vitrify it and recycle just what you need. Or maybe it's cheaper to recycle main fissile immediately and the rest maybe with 20 years delay. So saying that, there are 4 possible operations with liquid fuel. You can remove the salt from the core, which has no impact to the neutronics. You can clean the salt in the core like off-gas system. It has direct impact to neutronics. You can clean the salt outside of the reactor, no direct impact, and then you can refill the salt to the reactor, which is direct impact. So those are the 4 operations you can imagine, and all the MSR design are based on these 4 operations to a certain extent. And then you have recycling strategies. I will not go through everything, but you have salt removal from the core, continuous batch-wise, and from small amounts to full core load, in situ, ex situ, and so on. There are 2 extremes in these cases. One extreme is online recycling everything in situ and ASAP. The other extreme is offline recycling everything ex situ and with years of delay. So somewhere in between, you will find that all the MSR designs are positioned. Now I have example of fuel cycle studies for MSR, which I will not go through in detail, but for instance, it seems that the MSFR core, if you would stop to reprocess it, has positive reactivity swing because the thorium which you will consume will more or less overcompensate the fission products which you will create. So there is a good chance that if your reprocessing unit will be down for a while, that the reactivity of your reactor will grow. But I will not go to detail here. I have another study. There is a reprocessing technique called volatilization, which can be used to remove uranium, neptunium, and plutonium. And in this study, we assume that you can choose. You can choose if you remove just uranium or uranium and neptunium or everything, more or less. And what was interesting outcome of this study is that then, of course, it changes the fuel composition in the core, but it also changes the cumulative waste. If you recycle everything, then you have just reprocessing losses, and the cumulative waste is similar to the core loading. If you recycle uranium and neptunium, your waste is dominated by plutonium-8, and if you recycle only uranium, your waste is dominated by neptunium-7. This has consequences to your radiotoxicity in final repository, and this is the last slide, so it should be the most complicated. So you have differences between these decay curves, so recycling everything, only uranium, and this is uranium and neptunium. The initial difference is uranium-8 decay chain, then the middle place it's thorium-2 and uranium-5 decay chains, and at the end is again uranium-8 and neptunium-7 decay chains. To understand what I just said, you should look on the chains. So in this case, uranium-8 decay chain include plutonium-8. So it's mainly plutonium-8 which makes the difference here. In the middle, this plateau, it's plutonium-9 and plutonium-40, basically. And at the end, the bump again, it's, if you look on it, in one case it's neptunium which starts to decay, and in other case, here, it's also plutonium-8 which is decaying through radon and so on, creates also secondary bump. Yeah. So with the volatilization technique, if you can choose what you recycle, you can immediately influence what may go to final repository. So you can choose what is your wish. If you would like to be faster down here, or if you prefer lower radioactivity at the beginning or at the end. That's all from my side, more or less summarizing that sustainability of uranium-5 fuel reactors is not so long. We need to burn thorium-2 and uranium-8 catalytically, and solid fuel reactors have some issues, but okay, MSR has also issues, so I would be not so strict to say that everything will be solved. And there are several cleaning and reprocessing technologies, and the limiting factor for us typically are the thermochemical properties of the salt. We will have a lecture about it. And once again, MSR may be the only reactor to combine sustainability with acceptable safety, economy, and proliferation. Thank you.